We first finished what we started yesterday, just by a few, it's a comment of what we said yesterday. Yesterday was more about the principles, and today is a kind of application of these principles. So the principle was written by Kate. It's the fact that when you have an interface, you have a special energy, which is surface tension times surface area, and a natural consequence of this energy is the sphericity of drops and bubbles. And so this is something that we looked at yesterday. In particular, we designed solids which somehow repel water or oil, even oil, so that it satisfies this minimum of energy without taking into account the solid, because the solid was special, as we said. And so I would like to add two comments. The first is something that I like a lot. Well, it's something we have been doing for years and years. Actually, we left this subdomain, but it makes very beautiful pictures, and it's also a very direct illustration of this basic principle. So I show you the movie about that, which is about water repellency. And the second thing is also about dynamics, which is something which I do not really understand fully, but it's can we achieve this situation using dynamics and not looking at the dynamic consequences of this situation, which is quite different. So these are the two little comments I would like to add. So the first thing is really the picture which is there. So you remember that you treat your surface with something special, let's say little textures, it's hydrophobic, and you look at the impact of a liquid which comes on that. And this is a movie that we did recently for a very large public. It was for an international exhibition about water in Zaragoza, Spain. And so the quality is slightly better than my usual movies. And so you have a drop which is coming. The solid is treated to be very hydrophobic. And this little movie, which is short, however, it's a lesson in fluid mechanics. There are so many phenomena. There is probably one person on the planet, on the Earth, who can explain all these phenomena, who is sitting there, but he's leaving, unfortunately, tonight, so you cannot ask him all the details of this movie. But look at it. So the drop is coming, then it impacts the solid, and it makes beautiful layers. So it makes some kind of pyramidal shape. Slightly later it recoils, because it does not like this water. There is some satellite which detaches here, and then you have these beautiful waves. This is just water, and so the succession of images is of course very nice. There was a very little satellite here, and the second one, which was emitted. Look at the coalescence between both. It makes a little daughter drop, which comes back to the solid. So you have the big one and the little one. So look at the little one. It hits as a solid ball, while the big one is very soft. This is a consequence of the Laplace pressure. You see, a bubble was ejected and a little jet, so it's a singular event. Singularities at interfaces are a very interesting theme, and so on. So it's something which is extremely rich. I hope someone could write a song. You do notice that it's very hard when it's small. It's something that you can see when you make a real rain with multiple drops hitting this solid, so multiple size, multiple velocity. The phenomenon itself is, well, the solid is dry, it will remain dry despite all these impacts, but the detail of the impact depends on the size. Look at this blurred little drop, it's solid-like, and if you think about it, if you think about defining a kind of Young modulus, which is of course stupid because it's a liquid. However, you think about energy per unit volume, which is the units of a Young modulus, in the Laplace pressure. And you immediately understand that the smaller the drop, the larger the Laplace pressure, so the larger the equivalent of a Young modulus. It's something also which is very clear, which is the fact that the vibration of the drop and the time of this vibration depends on the size. And this is a direct illustration of this principle. Look at this formula. The unit in which we can measure the quantity gamma is Newton per meter, and this is the unit of the stiffness of a spring. And so, very naturally, we understand that these drops can behave as springs, and we know what is the stiffness. It is just gamma. So this means, for example, if we think about the oscillation of the spring, we know that the typical response time of the spring is the mass divided by the stiffness, with the square root of that. And this immediately explains you why, when the drop is large, so when the mass is large, it takes some time to oscillate, while when it is small, it's very quick and so on. So you can capture everything just by this single formula, or even simpler, just by this unit of your stiffness. And so it's, of course, useful to think of interfaces as kinds of spring. My second illustration, and there is a very nice little application of that, which was discovered by Professor Chen in Duke University about 1 year ago, which starts from a natural observation. So he looked at the figures of condensation on the leaves in the early morning. And so, of course, water could condense on these leaves. And he noticed that on the lotus leaf, the drops which remain are always very small, hardly visible, typical size 10 micrometers. Okay? While on the leaf, which is just close to this one, you have large patches of water. And so he had the idea to look at the condensation of water on these leaves with a high-speed camera under a microscope. And so the scale of these drops is precisely 10 micrometers, the largest scale that you see when you look at these leaves. And of course, the way these drops are growing is very natural by accretion of vapor, which is coming. But when two drops are sitting close to each other, they can merge. And they merge because there is surface energy which is lowered by making one drop instead of two drops. So you have two ways of growing for a drop, which is just getting some new vapor or merging. And so the event that you are going to see is here. And so you have two drops which are going to merge at this place. And look at that. When they merge, it jumps. It jumps very high, you see, and it comes back. But it comes back and then it bounces, as we understood. And because it bounces, you lose this drop. And so it means that when they touch, if they are large enough, but large enough in 10 micrometers, they leave the leaf, so to speak. And so, if you want to understand this phenomenon, you just write that, well, the typical energy that you gain there, which is the size of the drop, the surface area of the drop times the surface tension, was transferred in kinetic energy, rho v square r cubed, which is the most ideal situation that you can imagine. Of course, you can think of losses there, but I ignore these losses. You immediately find that the typical velocity at which this drop should take off is something like surface tension divided by rho r, which is a very interesting velocity. It's inertial velocity when you think about surface tension phenomena. And numbers are very interesting there. Surface tension of water is 70 10 to the minus 3. Rho is 10 to the 3. And the radius here is 10 to the minus 5, remember, 10 micrometers. And so you get something which is square root of 7. Fortunately, we calculated yesterday square root of 7. It's something like 3 meters per second. And so this ejection takes place at a velocity which is half of that. So really the order of magnitude is correct. And you understand that it's a very nice way also of thinking of these systems are systems which, despite the very small scale, somehow conserve energy, which is a remarkable fact. And there are many questions today which are dealing with the fact that they do not strictly conserve energy. And so the question is, where does this energy is, and what are the ways you dissipate energy, which are also quite unusual. Generally, it's in vibrations which decay by viscosity, but it's not direct viscous dissipation as usually with little drops. So my second comment about yesterday's talk is about now using dynamics to generate such situations. So I know at least two ways. One became quite famous. It's an experiment by Yves Couder about 5 years ago, where you take a bath of oil and you put a drop of oil, and so it should merge, but it does not because you shake cleverly the bath of oil at a frequency which is typically 50 Hertz, an amplitude which can be millimetric. And when you do that, the drop bounces forever. You come back 1 week later, it's still bouncing like this. And the reason, the qualitative reason, is the fact that well, you renew constantly the film of air, which is at the very beginning, of course, there is air between oil and oil, and the way you shake it brings some new material between oil and oil, and so you keep this situation forever. Just thinking of that, and not the developments that if Quere imagine, which is about the interaction of waves with drops, which are very fascinating, the conditions for generating that are not so clear. In particular, you need the bottom surface to be soft. It does not work on the solid, which is a pity because it means that if it did, we would just shake a little bit our windshields and it would be enough to repel all the rain. But it does not work. And the reason for that is not really clear because you need both materials to be soft. And so the conditions for the general condition for having that are not so clear. And so because I'm dealing with solid surfaces, I want to imagine another way to generate levitation using dynamics. And the experiment I would like to show you, well, we tried the first time with one of your former students, J.C. Berg, and we started a new program on that, so I don't really understand it, but I think it's worth mentioning this possibility. So here, you make the solid move, okay? And in this movie, the solid here, the substrate, moves in this direction. So it's a solid which is wet by the oil which is coming on it. It can be any silicon oil. So there is a pure wetting. And if the solid moves at a velocity which is here, as you see, 14 meters per second, you see something which is quite natural, which is the fact that when the oil contacts the solid, it goes through the solid, okay? But you increase a little bit the speed of your solid, and then you observe something which is quite different, which is first levitation, and second, a very slow drift of your drop, but the velocity that you see here is about 1% of the velocity of the solid. Okay? And so, of course, there is a viscous coupling between both, so we can understand this velocity. What is less clear is the reason why it levitates, and I have no real answer to that, except a vague hint, which is the fact that when you look at these drops, they are very asymmetric. And so very naturally, you can think of a lift force generated by the lubricating film in the corner, which is below. And so if you write such a force, which is really in classical textbook, you say, well, a lift force in this case should be related to the viscosity of air, which is a lubricating fluid, the velocity of the air below your drop, the size of the drop, and the angle, the apparent contact angle that you have, the corner angle that you have below the drop to the square. So it's very sensitive to this angle. Yeah?
So wouldn't there also be a thicker boundary layer because between the air that's attached to the surface?
Yeah, of course. Yeah, you have to think of this boundary layer. Yes. You have to know what is the region where you have the velocity u, which I assume everywhere here. Yeah. Yeah.
So I mean, that thicker boundary layer would provide more air support for the drop as well, right?
Yeah, absolutely. But here the boundary layer is thicker than the film that you can see here. There is a very thin film, and this thin film here is about 50 micrometers in thickness, and the boundary layer is thicker.
So you're saying there's a transition around that 14 meters per second?
Yeah, so it's very sharp, as you could guess, very well defined, and the question is exactly this one: what defined this transition? So I have no real answer to that except this possibility, which is if there is an asymmetric shape, we should have a lift on this drop. We know the formula for this lift. We even know, I think, I hope, what is theta, which is itself a function of the velocity. And I can give first an experimental answer. Theta is a function of the capillary number, which compares viscous force in the film and capillary force. And you have a scaling law, which is 1/3. And if you want to understand where it comes from, this is very close to a problem that I cannot not evoke in a course devoted to wetting and capillarity, which is the Landau-Levitch problem. The fact that when you draw a solid out of a bath of liquid, you entrain a thin film, and the scaling for the thickness of this film is capillary number to the 2/3, and the scaling for the transition region where you form this film is capillary number to the 1/3. And in this case, this is something which is very close because you draw a solid below your drop, you entrain air with this solid, so air is here, this is a liquid, this is a solid, So you expect something very similar. And indeed, if you divide this quantity by this one, you define an angle which is there, and you find the right scaling, CA to the 1/3. So you probably understand what is this theta, and so then you have a formula which is completely explicit for your lift force, and you can compare this lift force with the, for example, the force necessary to deform the drop, capillary force, or to the weight of the drop. And so very naturally, you end up with the idea that there is a threshold velocity at which you make this entrainment. Yeah?
But it seems as though the whole question is about whether or not the drop initially touches the surface.
Yeah. So here I assume that the film is there, but initially there is a kind of film because there is a gap, exactly like in the Quere experiment. So I don't explain the transient regime here. I explain that if I have a film, then I can understand that it's asymmetric and that it's enough to oppose, let's say, the weight of the drop. Yeah?
Do you expect that this effect will go away if you do this experiment in lower pressure?
Lower pressure?
Yeah, will the pressure of...
It's a good question, yeah. I will change a little bit the viscosity, but not that much, so yeah, it should work. Yeah? Spin? Spin what?
Drop spinning.
No, here it does not spin. No.
I mean, you couldn't see it spinning. If we're spinning, you wouldn't see it.
Yeah, it's a...
No, it's not spinning.
Yeah, it's interesting. Yeah. But here it's purely falling down, and so it's in foundation. We put tracers inside, and of course we have a little flow inside, at a velocity which is much smaller than the velocity of the solid. Because the viscous coupling is quite small. It's viscosity of air. So another way to say the velocity of the drift is much smaller than the velocity of the plate.
Which direction do you get the next spin?
It should be from forward
Yeah.
to the left on the bottom of the drop.
Yeah.
So it should be
Yeah, absolutely. Yeah. But now, if you come with some velocity, so if the velocity of the drop is large, so you add something, then you do not understand exactly what happened, but the movie is funny because it tells you that there is also a threshold of entrainment, which for a fixed velocity here, which is, I think, if I remember correctly, 15 meters per second, so we are in the high velocity regime, depends now on the velocity of impact. And this has to do with the initial formation of a film, which is enough to sustain the drop. So if you come across this film, you can touch. And so this is visible here, where we vary as a function of time the velocity of the impacting drops. And when you do that, first they are quick, and so they are entrained by the solid, and then they are slower, and then there is a very well-defined transition where they bounce off because you are below, now you reach this critical velocity. So this one has a nearly negligible velocity, and because the solid is so quick, it also bounces very nicely. So this is something which is quite open, but I think it's a good complement to tell you that, well, there are many things to say about this situation, either on a static point of view, which was more or less my point of view yesterday, or on a dynamic one where you can generate this unusual situation. Yeah?
I'm sorry, I said you shouldn't do experiments on falling bodies.
We should,
Are these surfaces textured or?
No. This is flat surface, completely weathered. So of course, yeah, this is very important because it's a very general case.
You said that the surface is weighted, but does that depend on does the behavior depend on the thickness of the film?
Which film?
Of the film that is below.
No, there is no film here. It's a pure solid surface.
It's a pure solid.
Yeah, it's this surface.
Okay.
It's a metallic surface.
It is wetting.
Yeah, it's wetted by this liquid. So there is, it's a complete wetting here. So I need something completely different to induce non-wetting. And this thing is movement.
Sometimes when we drop small droplets of water on a film of water,
Yeah.
you see the same stuff.
No, it's not exactly the same.
Okay.
But it's true that when we pour, let's say, coffee on coffee, it's a very good example because we see these drops which are running, let's say, at least 1 second before merging. And this might be related to two things. It's a very old observation by Reynolds, actually. The first thing is that there is generally a difference of temperature between the coming drop of coffee, which is generally hotter than the pot of coffee. And so these little differences of temperature induce very sophisticated mahogany flows, which are able also to bring air between. And this was very well studied by Neitzel in Georgia Tech. And the second effect is that, as we know, we can make a foam with coffee, so it means that there are surfactants, and so these surfactants can delay a little bit the coalescence. They make a kind of barrier between. So these are the reasons. So very different from here. So I started. Your introduction was extremely long. I think it was 15 minutes. As you. Okay. So now I switch to my part of today, which is unbalanced weather. So it's really a direct application of this formula, and it's a very general question, which is the following one. I take some liquid material, I put this material on a solid, and I want to see what are the tricks to generate a spontaneous self-propulsion for this liquid. And of course, this has to do with some asymmetry. If I deposit a drop of water on this table, there is absolutely no reason to drive it in the right direction as I assumed in my little sketch. And so I will give 3 examples. One is about wettability contrast, one is about mahogany propulsion, because we are a very good expert in mahogany things thanks to Kate, and one is something that I call surfing on a hotspot, which is a very nice challenge. So the first case is a bit academic, apparently, and it's the simplest way of thinking of this question is to say, well, if I have a solid which is hydrophobic on the left, hydrophilic on the right, there is a very well-defined boundary between these 2 domains. If I deposit a drop across the boundary, and if this drop wants to obey etymology, it should go to the hydrophilic place, the place which it likes. And so we have to check the ability of drops to obey etymology, and they do. They are very reasonable. You see, they are driven to the right, to the place which is hydrophilic. And of course, it's a bit disappointing because they stop once they are fully in the hydrophilic domain, which means that the maximum displacement I can expect is 1 millimeter, typically, the size of the drop. So it looks a bit academic and disappointing. But, however, it's interesting to think about this little motion. The very natural picture is the following one. On the left, it's hydrophobic, so high contact angle. On the right, it's hydrophilic, low contact angle. And we learned a principle about 1 hour ago, which is KHTB's principle. Gradients of curvature drive motion. And so this is really the case. We have difference of contact angle, so we have a gradient of curvature, and so we should have a motion. And indeed, we had such a motion, and indeed, it was going to the right. We learned from Laplace that the pressure is higher here than here, and so the back should push the front. However, if we look again at the movie, we see something which is slightly different, which is while it moves, I stop the movie, and the drop is nearly perfectly symmetric. Do not see any gradients of curvature. Of course, Kate's principle is correct, but what is not clear, what means the word motion? It can be inside the drop, or it can be a global motion. And in this case, there is no gradient of curvature, so it means that very probably, I don't know if this is true, but very probably at the very beginning my picture was correct, that the liquid was driven inside the drop in such a way that it made the drop symmetric. The drop is symmetric, but the contact angles are not the correct ones. You see, this one is too small compared to the one it should be, and this one is too large compared to the one it should be. So this is something that we learned yesterday from Thomas Young. It's a fact that when we think of a contact angle, it can be at equilibrium, provided that you have the right contact angle. So, for example, if I make a picture on the right situation, which is this one, so I observe the contact angle theta, and this contact angle theta is larger than the contact angle theta 1 that it should have at equilibrium. And so, I'm tempted to do the Young's construction. Remember, this is surface tension between solid 1 and vapor. This is surface tension between solid 1 and liquid. And this is surface tension between liquid and vapor. And I project these forces on the horizontal line, and I find a force per unit length, which is the following one. I call it F1. F1 is gamma S1V minus gamma S1L minus gamma NV cosine theta. But I can use Young's relationship to get rid of these quantities. And this is just gamma NV cosine theta 1 minus cosine theta. And because theta 1 is smaller than theta, this quantity is positive. So I'm very happy to understand that this part of the drop is drawn to the right, because it's not the correct contact angle. I could say that in a very qualitative way. The contact angle is too large, so the drop tends to spread, and to spread, it has to go to the right. So now I look at the opposite side, the one on the left, and I can do a sketch which is very similar to this one. I have an angle, which is the same, theta, but this angle now, theta, is smaller than theta 2, the angle of the hydrophobic part. And so I should have also a force, an unbalanced Young force, F2, which is directly calculated from this construction, and now I project on the horizontal, and I choose also the same positive direction to the right. And so as a consequence, this force should write gamma S2 liquid plus gamma LV cosine theta minus gamma S2 vapor. And again, I use Young relationship, and I find gamma LV cosine theta minus cosine theta 2. And because theta is smaller than theta 2, again, I'm very happy to find that this force is positive. So it means that the drop that you see here is drawn at the leading edge, and it is pushed at the trailing edge. Okay? And there is a kind of little miracle here, which is that if I add these two forces, which are both acting in the same way, I find a global force, which has a very interesting structure. It's gamma LV cosine theta 1 minus cosine theta 2. So it's independent of theta. And so even if theta varies, for example, as a function of time, it will not impact this quantity. It just reflects the contrast of weightability that we have at the beginning of the experiment. And it's a very nice expression because it's exactly the one you would have found if you come back to this picture. So the picture is wrong, but the force that you would calculate would be directly this one, because you are sensitive to this contrast. So it's a very nice thing, because it means that this intuitive way of thinking, even if it is wrong, gives the right answer, and so we can use it very conveniently. I'll come back to the mistakes that you can make slightly later.
So, do you know the determinants data?
Sorry?
What determinants data?
No? No, I don't know.
I mean, you just 73 points of view?
I don't know. Yeah, no, I don't know. Yeah, no, I don't know.
Because otherwise you wouldn't be a sphere.
Yeah, no, I don't know what determines theta.
I mean,
No.
isn't that the liquid, the type of liquid that you have?
No, that's the one that is too.
Yeah, no, I don't know. I know that theta, of course, determines the velocity at which the drop moves, because what you saw yesterday is the fact that if we want to balance now this ion force with viscous force, and the viscous force is dominant here because remember that we have this special line friction, which is always dominant in these systems, then remember it was sensitive to theta. It was inversely proportional to theta. So the velocity depends on theta, but what fixes theta? No, I don't know.
Have you compared the dynamic theta to the average of the two equilibrium angles?
No, I did not compare anything. It's just for pedagogy. It's not a research thing, but I think it's very useful to start by this, and even to realize that it's not that simple. Yeah, I saw someone. No, okay. So a direct application of that is this spectacular motion that is observed when you think about the how can I say that? I don't know the word in English, but it's a reproduction of mushrooms, the way they make kids, something like that. And so it acts with a spore, and the key point for a mushroom is to act in such a way that the spore will go far enough, okay, at a distance which is, I would say, at least the size of the mushroom. In which case, you can find a place which is empty, and so you can grow there. And it's a very painful question when you think about it. When you are a plant, somehow you have to move. And so how can you do that? And here it's really the point. You have to move to create a new colony of mushrooms. And you have to move by a quantity which is extremely large at the scale of the spore. The spore itself is visible here. You have to think of the hat of the mushroom which is there. You have lamellae here, and the spore is just attached by a very thin spike here, and the size of this spore is 10 micrometers. The spore is hydrophilic. The rest of the environment is hydrophobic, except one very little place, which is close to the spore, which is here, which is hydrophilic. Okay? As a consequence, where the air becomes humid, you have a little drop which grows at this place. Imagine that it grows also on the hydrophobic part. We understood that then it has to move to the hydrophilic part. So this is the first application of what I said previously. The fact that when you have a hydrophilic spot in a hydrophobic environment, and you have a vapor which is coming, you condense this vapor, and you displace the liquid in such a way that you fix the place where your drop is growing. And this place is very close to the spore. Okay? And so this drop is growing, and of course at some point it will touch the spore, and the spore is hydrophilic. And so as a consequence, the drop should jump on the spore. And so Jacques Dumais took these Xavier Gobelin, these very impressive movies a few years ago, where they spent, I think, months to expect this event under a microscope. The scale is very small. And what they saw is that when the drop is jumping on the spore, you see, you have an ejection which takes place at a remarkable velocity, which is of the order of a few meters per second. Why? Because of that, you see, you transfer surface energy in kinetic energy, and so the maximum kinetic energy that you can expect is the one which balances this gain of surface energy and transfer in kinetic energy, which is written here. And so if the size of the object is 10 micrometers, which it is here, you find a velocity which is about 3 meters per second, which is the order of magnitude of the velocity that we measured. And there is a very nice little calculation to do, which is, well, if you use this little catapult, because it's a capillary catapult, to move your spore, where will it go? And the little argument is very simple. You have to balance the inertia, and so density of the spore, volume of the spore, so this is the mass, v squared over the distance, and so here I wrote the inertial force, and L is my unknown, and this energy, or if you prefer this force, is balanced by a viscous force here, because you are at a very small scale, the velocity is not that high, and so the Stokes force is dominant. And so you expect here a force which is just viscosity of air, velocity times the size of the spore. And so you see a very simple formula which is coming from L, which is something like the Reynolds number, rho r v over eta a times the size of the spore. And so it's interesting to put numbers here. You have rho is the density of the spore, so it's 10 to the 3. R is 10 micrometers, so this is 10 to the minus 10. It tells you really this quantity that if you have a very small spore, it's very difficult to get a large L, of course. You see 10 to the minus 10, we have to fight against this ridiculous low quantity. V is 3 meters per second, and eta A is 10 to the minus 5. And when you do that, it's a miracle, you find that it's a few centimeters. And so here I find 3 centimeters, which is exactly the size, the typical size of the mushroom itself. So it means that this catapult is efficient enough to drive the spore at a place where there is a probability that there is some space, some nutrient and so on, and you can grow and move the colony of mushrooms slightly further. Very practically, also it explains why we find mushrooms, young mushrooms, after a humid weather. Because, of course, you need this catapult to be activated, and so for that, you need a lot of vapor in the atmosphere. So, we saw this first example where, despite the modest movement of this drop, you can generate quite a large effect, at least at the scale of the mushroom. But people thought of other ways of amplifying the distance at which you can drive drops using gradients of wettability. So one way which was developed in particular by Manoy Chaudhuri, I think when he was with George Whiteside, precisely, a few years ago, 20 years ago. And he did something like a backgammon game. So the hydrophobic part is the black one, the hydrophilic one is the red one, and so you have a continuous gradient here. The scale here can be, let's say, 10 micrometers typically. So it's of course far above the size of the molecule, but far below the size of the drop. And so this distance can be now a few centimeters, and so if you place your drop here, you expect that motion is possible on the distance, which is the distance that you chose a priori, which is the distance of your backgammon game. And so this is an illustration here, where you see the scale of the drop, and you will see that when it decides to start, for some unknown reason it waits a little bit. When it starts, very clearly it moves, and it moves on distances which are much larger than the size of the drop, and it's also very clear in this movie that the contact angle is decreasing as a function of time, because of course you are in regions which are more and more hydrophilic. And so, as a consequence, the velocity is also decreasing as a function of time because you increase the dissipation in this case. So this is one way, which is not so easy because it's something I shall come back later to that, but you have to treat your solid with different chemical species and so on, and so very naturally you generate pinning in this case. And so pinning, of course, should oppose any of these little forces that I'm describing. So there is another trick, or another category of tricks, which I like a lot, which consists of making a drop which is such that it makes itself the boundary between hydrophobic and hydrophilic, which means that it will construct continuously this boundary. So it travels with the boundary. And so the first example of that was found by Thierry Ondarsu 15 years ago. And this is a top view of a glass plate. And on this glass plate, Thierry deposited drops of octane. So if it were pure octane, it would gently spread on the glass. But it's not pure octane. It contains something else, and as a consequence, you have a motion at a very large scale, let's say 10 centimeters here, and then you can reveal the trajectory, and it's somehow random, not completely, in particular because it tends to follow the cosmos, as you see, but it tends also to avoid its own track. And the trick is the following. In this octane, you have a molecule which is likely to draft on glass. And so these molecules are very well known because they are studied and used by the glass industry to make the glass hydrophobic. So it's a covalent bonding. These are silanes, and they draft on the silanol groups of the surface of the glass. And so imagine that you put your drop of octane plus these molecules. The chemical reaction starts at some point, and so it means that below one part of the drop, the glass became hydrophobic, and so from this moment, the drop will tend to move away from this hydrophobic track. Which means that if, by accident, it comes back to a place which was already treated, it tends to avoid this place. So this self-avoiding walk is a direct illustration of the fact that you place something irreversibly on the glass. So, there is a variation of, yeah?
Can you do a statistics on this and see if it's a self-avoiding random walk statistics?
Sticks? What do you mean?
Statistics, I mean.
Ah, statistics. Yeah, so this is, so this is interesting.
It means that
it's not an easy question because it means that we would have access to the reason why it changes its direction to make it random. And so this depends on the surface that you have initially. Because you need some defects, of course, to push your drop to go in. For example, some hydrophobic defects which are on the glass should be enough to change the trajectory. So to have something which is really random needs to have a randomly distributed collection of hydrophobic patches. And then you could do the experiment that you are suggesting. But yeah, in principle it's feasible because this worked for a very long time. Because the population, which is in volume, is transferred in the surface, and so you can, of course, the number of molecules that you need to treat the surface is extremely small, because it's just one monolayer, and so you can generate motions at the meter scale, and so then you could do something like what you are saying, which was not done. So there is a variation of that, which is very recent, by the group in Kyoto University of Yoshikawa. And then I show you the movie before I tell you what it is. So this is a petri dish, 12 centimeters of diameter. It's filled with water, and Yoshikawa is going to place a drop of oil, which is heavier than water. So this drop will sink, and it will go to the bottom of the container. And then, as you can see, it self-propels. And there is something which is very interesting. So this is very random, I would say. And look at that. Here there is a little loop. And so it's not the same phenomenon. There is no self-avoiding characteristic here. And the reason is very interesting, and it tells you about something that you learned from Kate 2 days ago, which is the imagination of people who are designing this kind of physico-chemical systems. So this is a kind of qualitative explanation. So this is now a side view of the same experiment. It's not exactly the same because he put here 3 layers of glass instead of having a flat glass as in the previous movie. This is water, this is the oil, and there is something that you do not see and there is something that you see. What you do not see is the fact that in water there are surfactants. And these surfactants are positively charged, and so they tend to absorb on the negatively charged glass at pH 7. Okay, so the picture we can have is that this glass is covered by a kind of monolayer of surfactant molecules. What you see is the fact that oil is orange, and it's orange because it contains iodine. And this iodine has the ability to make a chemical complex with the surfactant. So it means that it's exactly the contrary of the previous experiment. In the previous experiment, the drop was depositing something. Here, it's already deposited, and so the drop tends to extract something. And this is feasible because it's not a covalent bond. It's a weak adsorption. Okay? And so if the chemical reaction, if the extraction starts here, then this part becomes hydrophilic, this part is still hydrophobic, and so you should observe a motion in this direction. And so this is what you can see from the side now. It starts because it kind of reset. And once it is at the top, it remains forever, and it makes a movement, which clearly tells you that it's not self-avoiding. See? And the trick is very simple to understand. Remember that you have a large collection of surfactant molecules here, and so once the drop has left, there is this possibility of healing the damage which was done to the surface by the drop. And so you regenerate constantly the surface until your iodine is completely saturated with surfactant, which takes minutes. So you can observe the motion of this kind for a very, very long time. So it's a very nice experiment, and it tells you, again, the imagination of the people working in the field.
Excuse me, could you please show the previous movie?
Yeah?
So here, when you put the drop and then the drop starts moving like randomly, I was thinking the wetting between the oil and water, I mean, we don't know how it is, if it's non-wetting, if it's partial wetting, so you can actually leave something, like, I don't know, some little oil behind you, like it's like a tail, and then those are the defects, that's why it does.
It's a very good question, because if you want to understand the dynamics, and even if you understand the way it works, you need to know something about the contact between the solid and the liquid and the possibility of exchanging the salt molecules.
And even the liquid.
And so I would say that it must be partial wetting, because if it were a complete non-wetting situation, then you have no contact. The oil is always separated from the solid by a thin layer of liquid. We'll come back to that slightly later, actually.
Okay.
And then there is no possibility of exchanging material. So it should be partial wetting in this case. Yeah, so very little variation on that. No, because I show it because it brings something new. Of course, another way to build a gradient of wettability consists of having a gradient of texture. Remember that you can also play on the wettability by putting some texture. And we saw that the principle is that if the texture is hydrophobic, then this tends to detach the liquid from the surface. And of course, the larger the density of pillows, the less hydrophobic it is, because hydrophobicity is a function of the quantity of air which is below. So if you have a region where you have a very small density of pillows, which is the case here, the pillows are very small because the scale here is very large. Below a drop that you put here, there is mainly air, 99% of air and 1% of pillar, while at the top you have 10% of pillows, so you have only 90% of air. And so it means that drops are, so solid is more hydrophobic here than here, so there is a gradient of wettability, which is not brought by chemistry, but by physics. And so the question is, does it move? Does it move to regions which are not more and more hydrophilic, but less and less hydrophobic? And so this is the experiment. You put a drop on the place which is very hydrophobic, and this is slightly less hydrophobic because you have more pillars. And this is a movie, and you see nothing happens. And the reason is very interesting. There is a force. We know that there is a force. We have the formula for this force. It's here. And it tells us that we have a contrast of wettability, but nothing happens. And this is very general, actually. In most cases, when you do such an experiment, nothing happens. And the reason is pinning. It's something that I did not discuss up to now, the fact that drop sits on solids, okay, but they also pin on solid. You have defects, and here, in this case, you have defects. You put these defects. These are the pillars. So you have possibility of pinning. You mentioned this possibility, the fact that when you have these little cylinders, you mentioned the fact that they have corners, and on corners you can pin, and here, even if you have only a few pillars, it's enough to oppose the force which is written on the blackboard. So this is very sad, but because it's also very general, you have to think of how can we deal with such a situation? What are the tricks where we can oppose the pinning? And I just mentioned a very elementary trick, which consists of shaking a little bit the solid. So you shake it a little bit, and when you do that, suddenly you are very happy because indeed your drop is moving in the direction that you were expecting. And so then if you want to think about this movement, you can first think very qualitatively. You say, well, when I shake the thing, I allow deadening to take place. So this is a very sentimental statement. And so as a consequence, the force should enter. In this case, the reason is slightly more subtle and quite interesting. It's the following. I take the same surface, so the same material, so the gradient of density of pillars, and the drop is coming, and my question is, does it bounce, as it was bouncing at the beginning of this lecture? And the answer is the following. The drop is coming. Yes, it does bounce, but it bounces obliquely. You see, I show again the movie. It's not a specular impact, as it was. It's an oblique impact. You see? And the reason is funny, because when you look at the detail of the impact, the drop is coming. Then, of course, it transfers its kinetic energy in surface energy. This is the formula. And the balance is written here. So I'm very lazy today. I wrote two formulas, and it's enough for 7 lectures. And so I know, more or less, what is the size of the pancake that I make for a given velocity of impact. And so, as you can see, this, for millimetric drop, this size can be typically centimetric. But below the drop, here it's very hydrophobic. Here it's less hydrophobic. And so, as we know, as we saw, these drops tend to recoil, and the velocity of recoiling, or the velocity of dewetting, depends on the driving force. And the driving force should be larger here than here, because here it's more hydrophilic than here, phobic than here. And so I expect V2 to be larger than V1, and this is indeed visible. A few milliseconds later, this part moved by a large amount, and this one did not even move, because it's spinning. And so, as a consequence, I am transferring in this experiment vertical momentum in horizontal direction. And so now, if I come back to the previous example, when I shake something, it's like varying the gravity, it's like modulating the gravity. So I expect my drop should spread a little bit, recoil and spread and so on. For each cycle, I expect something like that. But now I understand from the impact experiment that for each cycle, I should observe a small displacement in a ratchet-like motion of this part, which is a more hydrophobic. So look at this movie again, thinking of that. So for each cycle, I see here that this point indeed is moving to the right. And so I see that it occurs only in the dewetting stage. and I understand that the origin of the propulsion is slightly different, but more interesting than what I could feel very, very qualitatively. So now, I would like to switch to a second general case where you induce self-propulsion of liquids. And this second case is based on the second source of asymmetry, which is, I think, very simple to draw, but not so easy to achieve, which is the following one. So I need two colors. So I have my solid, which is there. And for the moment, I played on the solid. I chose solids which are not homogeneous. Okay. Now I would like to play on the liquid. This is the second possibility. And I draw something which looks difficult to make, which is a liquid which is pink here, and which becomes green here. And if I invoke Kate's principle, it's a slight variation. The curvature is constant here, but as she said, the surface tension is different because they are not the same liquid. So because pressure is surface tension divided by radius, here I do not play on the curvature, but I play on the surface tension. And so if the surface tension of the red part is larger than the green part, this should make a motion in this direction. And so the question becomes, how can we do such a hybrid drop, something which is pink on the left and green on the right. So there are probably many ideas that you could have about that. I know only two examples. So the first one is to juxtapose two drops in a tube, in which case you avoid something that you would have if you put this experiment on the plane, which is the fact that immediately one drop chooses to go around the other one. And so it stops everything. You end up with something like, again, like a fried egg, where you have, let's say, the red part at the center and the green part around. But here, you avoid that because you are confined. And so there is no possibility of surrounding. The two liquids are obliged to remain close to each other. Of course, you have an intermediate frontier here, but you have a difference of nature of the liquid between both sides. And so this is something that you can see here. So you have the red oil, and then you juxtapose the white oil. You put the whole thing on the table. You look from above, and you see that it makes a little train. And you have a car and a wagon, and it goes until it reaches the end of the tube. Okay? And of course, if the tube were closed, it would stop after one turn. So what is the origin of the motion? You can think of it by different ways. One, which is a bit magic for me, which is pressure. And so you say, well, if the surface tension here is larger than this one, the Laplace pressure here should be lower than this one. And so pressure is larger here than here, and so it should go to the right. And this is the only trick in this experiment. If you want to show it to your daughter or sister or mother and so on, you must choose as the first liquid the one of higher surface tension. Okay? And that's it. Then it should go. So it's a bit magic, and indeed, if we come back to the movie, you can notice something, which is the fact that the wagon, after a while, becomes pink. Do you see it? So it was white originally, and it tends to be colored. Okay? And so the reason is that there is some fuel in this experiment, so there is movement, and the fuel is the car itself. Okay? So it leaves something behind. It leaves something behind because of the Landau-Levitch principle. The fact that, or if you prefer, it's even simpler to say that like this, you have a no-slip condition at the wall of the tube, and so because you have a displacement of the red thing, it has to leave something. Okay? Which means that the surface of your tube is affected by the motion. And so this is the kind of picture that you can make, where you draw the train at a given moment and slightly later. And what we could guess from the movie is the fact that you leave something behind, and so it means that the surface of the tube was changed by the motion. And so you can compare the surface energy just by applying this magic formula. You change the nature of the surfaces, and so you affect the surface energy. And if you do that, you find exactly the force that you would find by the pressure argument, which is of course satisfaction. So a little variation on that, because you heard about surfactant, and just to tell you that these things can be very subtle, is the following idea. Well, now instead of 2 cars, I have only one, which is made of oil. Around, I have water, and on one side of the water, I place surfactant. And so this should be more or less equivalent to the previous situation, because in this case, the surface tension of the water oil should be affected by the presence of surfactants. Okay? And so I expect in this situation that surfactant adsorb on this surface, and so there is a difference of surface tension. Here, I did not represent the menisci, but they should be of the same curvature, because it's inside the tube, inside the pore. Of course, you can think of this experiment as a very model experiment for detergency. In detergency, you have pores, you have oil inside the pore, you try to get rid of the oil, and precisely you place some surfactant. And so you expect that this surfactant should induce a motion of the oil. And very, very ideally, you expect that this motion should completely clean the pore of its oil. So this is the experiment. So everything is in water, like in a washing machine, and you have the tube, which is a pore, so 1 millimeter here. This is the oil. It's a non-wetting oil, in this case. Surfactant is brought here. Of course, you don't see it. It's a molecular thing, and there is pure water. Okay? And you look at the possibility of a motion, and indeed it moves in a direction which maybe you guessed, and then it reaches the end of the tube, and fortunately, it comes out very nicely. The first drop, and the second one, and there is a little quantity which remains, but even this little quantity, as you see, makes some effort and comes out. And so it's a success, considering the fact that you try to get rid of the oil. At the end of this experiment, the tube is empty of oil, and filled with water. And so the first thing you can say about this experiment is that it's nearly trivial, because you see, surface tension is lowered by surfactant, so low surface tension here, high surface tension, pressure is the same because it's a tube which is open at both ends, and so when you cross this interface, the pressure is higher here and here, and as a consequence, this part pushes this one, and so it has to move, and when it goes out, you make something which becomes large, and so the pressure is even smaller, and so it has to go out. Yeah?
You mentioned detergency, but in the washing machine, wouldn't the surfactant concentration be the same one built in?
Yeah, no, of course. This was a very ideal situation. In washing machines, the surfactant might come equally, and if you do that, if you of course make a situation which is symmetric, you do not observe anything. I shall come back to that slightly. But now you can think of something which is an obvious limitation of what I did. And I'm cheating when I'm showing this movie. I'm cheating because what you expect is that you can only displace this drop by 1 unit. Why? Because as we know, there is a little film of water here which can transport surfactant. And so once we made this 1 unit displacement, we are exactly in the situation that he said. We have surfactant here, and so the motion should stop. And so where I cheated is that I chose a length here, which is larger than this one. And so, of course, it had to work as if it worked forever. You see? But I realized when I think about that it should be a very limited displacement. So, we are scientists, so even when we have ideas, and even when they are simple and seems correct, very often we try it to see if this is correct. And in this case, you are going to see that it's not really correct. It's more interesting than that. And it's a movie where there are many things to see. So in this movie, you are exactly in the situation where the length of the tube is much, much larger than the size of the drop. Okay? And in addition, we organize a little race, like yesterday, but now it's not between a big and a small. It's between a viscous, this one, and a non-viscous one. So these are silicone oils, they are the same amount of surfactant, same water, same tube, same everything, but this oil is 100 times more viscous than this one. So it's a big, big difference. And because we expect dissipation inside the oil, we expect this one to be roughly 100 times slower than this one. So this is not fair. It's like organizing a race between two people who are the same, and we attach to one of them a very big ball of steel, you know, which is a viscosity. However, we do it because we are interested in these kind of stupid things. So this is the movie. Many things occur at the same time, so look at it. So, you see, we have a fable in France which is called The Hare and the Tortoise. And this is very similar. Because we have a kind of hare who makes jumps, quick jumps. In particular, at the very beginning, it was extremely quick and efficient. But we have a tortoise which is very, very slow, much slower than the hare, indeed. But at the end, it wins. So this means that the dynamics itself impacts what's happening in a sense which is very interesting, because first, we can displace these oils by distances which are much, much larger than 1 unit. And second, the dynamics can be unexpected. It can be either intermittent or continuous. So I show it the movie again. So I stop it after just 1 second. So you see, first jump, it's typically 1 unit of length. It's visible here, because this one hardly moved. And you see this one is just one unit ahead of the first one. So what I said is correct. The fact that once you reach this position, because you transferred some surfactant here, then you stop the motion. And you are in the symmetric case that you have. Okay, but here, you have a lot of water, which is pure. And so you have some diffusion which takes place. And so after a while, there is a possibility of setting again a contrast between both sides. While here, because you are slow, it's an advantage to be slow here. The film, which is there, is much thinner. Remember the scaling that I wrote and I erased, which is that the thickness of the film should be sensitive to the velocity to the 2/3. So if the velocity is nearly linear in velocity. So if the velocity is 100 times smaller, the thickness is 100 times smaller, which means that the quantity of surfactant that you bring behind is so low that it is diffused in real time. It gets diluted in real time. And so there is a possibility of generating a continuous motion in this case. And so as a consequence, because it's continuous, it's slow but continuous, the slow one is not only continuous, but it's quicker than the one which makes these jumps and it stops. So it's a kind of stick-slip phenomenon on the liquid here. I'm supposed to finish at 15 minutes. Yeah, okay. So when you think about surfactants, you think also of surfacers. I mean, liquid vapor interfaces. And then it's a bit different. As Kate said a few minutes ago, then you create a kind of pressure at the surface of water. And so this pressure, this gas of surfactant, is of course likely to exert some pressure. And if you exert some pressure, you should generate a motion. And there are these wonderful toys which are called Camphor boats, where you have a little piece of plastic, it floats on water, so this is a track of water, and at the rear of the boat you attach a little piece of camphor. So you see probably vaguely that there is something white here, and it's a kind of surfactant. Okay? And so when you do that and you make a movie from above, as done here by Nakata from Hiroshima University, you have this beautiful motion. And this motion is very beautiful because, of course, as you can see, you can make many turns. Or, said differently, if you have a green one after the blue one, the fact that the blue one deposited something does not prevent the green one from moving. And the trick is quite similar to the one where you could heal the surface damaged by the motion of the oil in the Yoshikawa experiment. Here, camphor sublimates very quickly, and so after a very short moment, there is a track which is empty of surfactant behind the. So Nakata did a very, very funny experiment. I cannot resist showing it to you, which is the fact that now you can imagine boats which have different speeds. And the way to do that is to change the thickness of the plastic, something like that. So if you decrease this thickness by a factor of 2, you decrease the drag by a factor of 2. And so, as a consequence, it should be maybe twice faster. So this is the experiment. So in this experiment, it's like in a highway in France or in Italy. The quick one is very close to the slow one, thanks to caution. And you know, in this narrow part, there is no way. I mean, he cannot do anything. But there is a possibility for overtaking in this part, which is about twice thicker than this one. Okay? So the question is, what will happen? And the answer is, I think it's really wonderful. It's this one. It does overtake, you know? And not always, not here, but here, and it's perfect. The timing is perfect, you see? Look at that. So, how does it do? Well, Nakata does not know, nobody knows, because you need a kind of force, maybe it's centrifugation, I don't know exactly the reason, but it's a very, very funny thing. So, this is real time. So, this is also a very natural motion that you can generate by using surfactants. And there are bugs who are using this kind of motion. So this little bug walking on water, this water has dust on it. The scale, which is here, is 5 millimeters. Okay, so this tells you the scale of the bug. And this bug here is touched by a little stick which is there. And so it became very afraid suddenly. And this one has a bag of surfactant behind. And so it releases some surfactant. And this is slowed down by a factor 50. So it's a very quick motion, very efficient. After which you get displaced by a quantity, by a distance which is a few times the size of the bug. So it's a very, very nice way. And if you imagine a predator which is coming here, there is even a possibility that now this water is polluted by surfactant, and so it's wetting water, and it should sink maybe behind. A little bit like in the movies by James Bond when he leaves some oil behind, and so the car which is going behind is away. So I would like to finish with something which is a kind of challenge, and as Kate did, it's something on which we are working recently, so I'm very sorry about that. So generally, scientists cannot resist showing what they are doing. But this case is interesting because first, it's a very beautiful question, which was raised by Heinerlink a few years ago, which is, can you induce self-propulsion without contact? In all the examples I showed, you need a contact, because you need exchange, you need asymmetry, you need things like, you need wedding, you need... But if you suppress the contact, if you are in this situation, the trick should be very different. And the situation that Heinerlink chose is the Leidenfrost situation. The one where we know for sure that there is no contact. There is a cushion of vapor, the drop is levitating, and so there is no possibility of any contact between the solid and the liquid, by definition. However, he made this experiment where you have a solid, let's say 300 degrees, you place a drop of water, and you look from the side, this is real time, and you see that these drops are going all in the same way, all at the same speed. This speed is quite quick, it's about 10 centimeters per second, and this is, of course, a direct illustration of something that I said yesterday, which is the fact that in this highly non-wetting situation, even a very small force is enough to induce quite a large velocity, because there is very, very little friction.
What is your surface?
What is the surface? Of course, there is a trick on the surface. And this trick, which you do not see at this magnification, is that the surface is decorated by some teeth. Okay, it's a ratchet. Okay, yeah?
Couldn't you do something similar with the thermal gradient?
You asked a very painful question too, because we thought about that, and we spent a few months with a student of mine, and L'Orbiance, trying to place levitating drops on surfaces where you have a gradient of temperature, but it levitates everywhere. Okay, so let's say 300 degrees here, 400 degrees here, and you place a drop. And we never observed anything, despite the fact that, for example, the temperature impacts the thickness of the film. And so, if the thickness is not the same, you make some kind of asymmetry, and so you might generate some motion. So we never succeed in doing that.
I would think you could also excite some sort of a Marangoni.
Yeah, also, you have mahogany. Yeah, so mahogany is subtle here, because when the temperature of this guy is 300 degrees, the temperature of this one, its water, is 100 degrees. So it fixes at the boiling point. And so inducing differences of temperature is not that easy. However, people showed that there is a small difference of temperature by a few degrees between the bottom and the top, because this is 20 degrees. And so there might be a possibility of generating mahogany flows in such a situation.
Look at the lumps on that.
Sorry?
The drop has lumps.
The drop is?
The drop has lumps.
What?
Irregularities.
Yeah, so there are irregularities. Yeah, you're right. And so now I show you the movie corresponding to this picture, okay? And this is a movie. So it goes at this nice velocity. You have indeed some kind of waves which are propagating around the drop. You have also some bumps below. You have a few bubbles. What else? You have some kind of slight oscillations. And so there are so many reasons for this drop to move. And even so many reasons to move in this direction, because the direction is very clearly defined. It is always a direction such that the drop climbs the little step. So of course, it does not climb any step because it's horizontal on average, but it's always in the direction of the step. Which, by the way, is something very interesting because it chooses the direction of the higher friction. Okay, this is something that we realized very recently. The friction is also modified by the existence of this texture, and as you can guess, the friction is higher in this direction. So it chooses the direction of the higher friction. And so you are with this situation. There is one student here, Hervé, who is there, Hervé, who was the very first in our lab to study this situation, and he realized something which we'll come back to that slightly later, that the force which is acting on this drop depends on the size of the drop, okay? Which is a very useful observation. But the question is, how does it work? And so I put in my lecture notes a statement about that, which is how can we avoid tons of calculation with an experiment? Unfortunately, we did not avoid the tons of calculation because we considered all these possibilities, waves, oscillations. We made the calculation and we always found reasonable possibilities for driving the liquid to the right. Even mahogany possibilities also, all of that. And one day, after 1 year of these very useless calculations, we realized that all the scenario we had in mind had to do with the liquid nature of the drop. And so suddenly, it changed a little bit our way of thinking. Does it work with a solid? And so the question is, can we find a solid which is a Leidenfrost solid? And the answer is very easily yes. If you think about what is called dry ice, carbon dioxide, it has a wonderful property, which is first, it sublimates directly at atmospheric pressure. There is no liquid phase, so this is why it's called dry ice, precisely. And secondly, the sublimation temperature is minus 80 degrees. So it means that if you place a piece of dry ice, typical size, the size of a coin of 1 cent, typical price of the experiment, 1 cent, precisely, so the price of the piece of dry ice. If you place that on a solid which is at 100 degrees, it should levitate. Okay? And so you do this experiment, you take a piece of dry ice, you place it on a hot ratchet, and when you do that, you find that indeed it works. So this has nothing to do with the liquid nature of this body, the fact that we see waves, the fact that we see bumps, the fact that we have downwind flows, all these possibilities, which are very interesting, do not necessarily explain the movement. If now you choose the wrong direction, so you take the piece of dry ice which is levitating and you push with your finger in the wrong direction, you see the following. So here it comes, so in the wrong direction because you pushed it. It slows down, this is very, very, I think, obvious. It makes what I would like to call a U-turn, and then it comes in the correct direction, which is the direction of climbing the little step, remember. And so we were first very happy of that, And then we try to think about the force, because now we know that it should be related to the production of vapor. And the fact that this production of vapor, this flow of vapor, has to interact somehow with the texture. Because of course this does not work on a flat substrate. And so here, something interesting happened, which is that first we built an experiment where we measured the force. And this experiment is something for people who like fishing. You know, you place a fishing line and you try to catch this fish. It's very easy actually. It's for a beginner in fishing. And so then you feed the drop. So it's a very large drop, and you measure the deflection of the fishing line, okay, and it tells you what is the force. Okay? And because the drops are evaporating, the movie is speeded up by a factor nearly 50 here. The size is changing as a function of time, and you look at the way this distance changes as a function of time. And it's quite obvious that it changes in such a way that the smaller the drop, the smaller the force. Okay? So it tells you that you have a force which is measurable first, and secondly related to the size of the drop. So this is something that you can plot, and you find that this force is on the order of 10 micronewtons. So it's a very small force, much smaller than the weight of the drop. And this is interesting again, because it tells you that without any appreciable friction, even a tiny force is enough to make a significant displacement. Yeah?
Did you ever change the angle of the ratchet?
Yeah, no, it's very difficult to build this ratchet. So the question of the design of the ratchet is very interesting, because the ratchet both impacts the possibility of motion and the friction. And so the question of optimizing these things is really open and a very interesting question. So 10 micronewton, and then find a kind of scaling law, which is this one. Okay, so it increases with the size of the drop to the power of 1.5. So I like a lot scaling laws. They are very useful. They capture generally the essence of a problem. They give us some very useful hint about what is going on. But in some cases, they can, how do I say? Mislead us, yeah. And this is one very good case. So, I would like to write a few things about this Taylor system. And the idea that we had, quite naturally, I would say, is the following. This is a ratchet. You have gas below. This gas is pressed by the weight of the Leidenfrost body, and so you have a flow of vapor. And if you have no ratchet, if it's flat, this flow is isotropic, and the key idea is to say, because you have a ratchet, you rectify the flow. And it's quite natural to think that you rectify it in such a way that the gas is mainly ejected in this direction, so that you can expect a kind of rocket effect on the ratchet, and so it goes in this direction. In which case, you expect the force to be related to the velocity of ejection and to the production of mass per unit time of vapor. And so if you want to understand quantitatively this phenomenon, you have to understand these quantities. So these are my final equations. So this is a solid. This is the body which is levitating. The size is r. The thickness is h. And the first thing that you can write, because you have a velocity, typical velocity u, is the fact that the mass produced per unit time is the density of vapor times the velocity times h times the perimeter, which is r. This is the first thing that you can write. The second thing that you can write is the fact that the mass which is produced by evaporation. So it should be sensitive to the difference of temperature between the ratchet and the Leidenfrost body, which is known, divided by the thickness of the film, times the surface area on which heat exchange is permitted. And you have here a constant which is related to the property of your gas. And the third thing that you should write is the fact that this mass, of course, flows because something is pressing on it. Okay? And so you expect, because this is very thin, you expect to describe this flow by the lubrication approximation. So the mass should be sensitive to the density of gas, to the cube of the thickness of the film, divided by the viscosity of air, or vapor, time the perimeter of your coil times the gradient of pressure, the driving force. And the gradient of pressure is the density of the body times G times the thickness, which is always given. Either it's a platelet and it's given, or it's a big drop and it's a capillary length. So it's a constant, okay? It's a distance which is constant, divided by the size of the platelet. And so in a stationary state, these fluxes should be the same. And so from that, you immediately find 2 or 3 things which are quite interesting. The first one is the following. If you balance these 2 things, you find that the thickness to the fourth is the radius to the square. And so it tells you that there is some distance, which is defined by all the constants, times the radius to the 1/2. It's interesting because it tells you that when you have these levitating objects, the thickness of the film, which I said yesterday is typically 100 micrometers, you can calculate it, and indeed you find 100 micrometers. But as the liquid is evaporating, it tends to become smaller and smaller, and the film tends to become thinner and thinner. And there is one point where a Leidenfrost drop meets the substrate. It is the ultimate point. It is when it dies. You know, when R is 0, H is 0. So this is the only case where you have a contact. So we can really say that there is never any contact. So the second thing that you can write is once you know this variation, you inject this variation here, and you find that M, the derivative of M, with respect to time, is R to the 1.5. And the third thing that you can write is that you know this scaling for M dot, you know that H is R to the 1/2, you have R to the 1, and so the third thing is that U is R to the 0. Okay? And so you know everything. In particular, if you think of the way the force depends on the size of the drop, indeed, you find that because this is independent of R, and because this is R to the 1.5, you find the right formula. So this is interesting because it can really mislead you completely, because everything works. It works so well that you can publish in a fancy journal all these results, which we did about 1 month ago. And, it's interesting. Michael asked me what's new with you, and I said, something interesting happened to me. I published something which is wrong. And he said, oh, great, we do not have enough wrong papers, which is I think, true. So now I'm very proud to tell you that I did something which is wrong. This wrong thing is written here. Why is it wrong? Because, as experimentalists, we should have checked everything, which we did not. We tried, actually, but it was difficult to do. Which was to look at the detail of the flow between the liquid or the solid and the substrate. Okay? And this is something that you can do quite easily, after some time. If you have this hot plate, the platelet of dry ice above, you put some backlighting, so you see the thin layer of paper, and you place first some little beads of glass. And so this just tell you what is the velocity when you approach the piece of dry ice from the hot substrate. And when you do such a moving, it looks a bit vague, but you see clearly these particles which are going that way here, and which are going that way here, because this is the center of the device. Okay? And so when you look at the flow, you find that in this direction, it goes at a well-defined velocity, which is of the order of 10 centimeters per second, and in this direction, at a well-defined velocity, which is also of the order of 10 centimeters per second. Okay? And so now you add a ratchet. Okay? So you put a ratchet, and the question, which is very crucial, is does the ratchet really rectify the flow? Which was absolutely essential as an assumption. So this is a ratchet. It's here. This is a piece of dry ice. Light is behind, so it's really in the Leidenfrost spirit, remember, the candle that you put. And you have these little beads of glass, which are in between, and you look at them. And when you do that, it's quite clear that they all go in the same direction. I think it's quite clear. And indeed, if you do a histogram of that, you see that there are very little particles which go in the direction. Most of them goes in the other direction. So first, you are very happy because indeed you rectify the flow, but you rectify the flow in the wrong direction. remember that I assumed that it was going the other direction. And so it means that the mechanism is not the same. It's even much, much simpler. But going to simplicity is something which takes generally years and years, which, well, this is a good case. And the scenario is very different now. It is to say, well, I have a rectification of the flow, it goes in this direction, and so I have a viscous drag on my solid above, and this viscous drag should be viscosity of vapor, velocity of the gas, divided by the mean thickness of the film, times r to the square. And here there is a complete miracle, which is the following. U is independent of r, h is r to the 1/2, this is r to the square, and so you find exactly the same scaling. And if you calculate orders of magnitude, you find exactly the same orders of magnitude. So this is one case where two arguments which were opposite give the same result. It's a very interesting case. Yeah?
I was going to ask about the 3 factors, but you answered it.
3 factors, yeah, they are the point.
But there's still, I mean, should that be corrected by that effect? Or
So, yeah, no, it's a very good point. So both could exist, and I think that in practice, there is it might be inside the prefactors, because of course you have two forces which are opposite, yeah, you're right, and so it's not completely clear why, but what is crucial is the direction of the flow, and so once you know it, you know what is the origin of the motion.
Well, you know the answer from the experiment.
Yeah, you know the answer of the experiment, but not only, you know the answer of the scaling, so you can express quantitatively, but the remaining question is how can you incorporate the previous scenario? Yeah?
Is there a difference for drag in a barbed hose?
The difference of drag between?
In a barbed hose. So you make a hose with barbs on the inside.
The hose?
A hose.
Actually, you.
Where?
So you have a hose
Yeah.
with barbs on the inside. Is there a difference?
It increases. It increases.
In a tube. Tube.
Yeah. A tube with barbs on the inside. Is there a difference in drag?
Pipe flow with roughness.
There is.
Pipe flow.
Someone made a pump where you just move the top, and if you have little ratchets, then you can fill the other side of the channel, because each time
cycle the water.
Yeah, so.
the water moves easier out.
Yeah, so, yeah, okay. So, indeed, Young in New York University did an experiment which is quite close to that. He took a flat piece of solid here, a ratchet, and he oscillated the flat piece like this, okay? And there is a critical Reynolds number, above which you see a flow which is in the direction that I assumed previously. But this critical Reynolds number is 100. And now, once you measure everything, you can calculate what is the Reynolds number in this experiment. It is of the order 1. So it's not enough to induce the flow in the direction. So it's not inertial enough, if you want. Yeah?
Did you also calculate the lubrication pressure in the gas and then get the horizontal component from that lubrication pressure?
Yeah, no, we didn't do that. This is last week actually. But it should be interesting because of course there are some variations of the thickness in this problem, and so we have kind of corners, and so everything should be modified by the result of this problem. So it's finished. Why is interfacial hydrodynamics interesting? So I think it was worth asking the question. The first thing I would say is we have a multiplicity of geometries and of scales, and the interplay between scales, a little bit like in turbulence, is something which makes the question very interesting. In all these examples, you have macroscale and microscales which were playing together. A key point for me is the variety of boundary conditions. You have solid liquid interfaces with a classical no-slip condition. You have a liquid vapor with a no-stress condition. You can add surfactant, and so you are in between. And we saw that texturing a solid changes the boundary condition. You can induce slip at a very large scale. So you have really many possibilities for the boundary conditions, which of course are crucial when you think of hydrodynamics. You have this large spectrum of Reynolds number. This example, last example was a very good one, where the Reynolds number matters because it decides the direction of the flow. And it could be either one or the other one. And also you have unusual driving forces. We are used at our scale to gravity, of course, And we understood that at the scale of these drops, gravity does not matter, surface tension matters, and so this changes, of course, the things, and you can generate non-intuitive phenomena. And as an example, a final example of a non-intuitive phenomenon, I'd like to show you an experiment which was done by Philippe Brunet when he was a postdoc with Densegers in Bristol, where he looked at the way a drop goes down an incline. As I told you, it's not such a trivial experiment in the sense that the friction is not completely obvious, but the slope is large, the drop is quite large, and so very naturally, this drop is moving down. Okay? And then he tried to understand how shaking this solid can change something. For example, about the velocity of this drop. So he shook, you said, this solid. And so this experiment now really looks stupid because the drop is away, but he shakes more and more. And it's a vertical way of shaking the drop. And, well, we have to wait, I think. But suddenly, the drop is coming back, you see? It's coming back, and bravely, it is climbing this high step, high slope, and it does that until it disappears again. Thank you.
Appropriate last set.